Hello friends, today's lecture we will now go to slightly different properties. Till now we concentrated mostly on mechanical properties of the material. Okay. Now we want to see some other properties, for example electrical and magnetic properties. So today's lecture will be concentrated on the understanding of these properties which are used in some of the application for materials. Of course, for a mechanical engineer it will not be of that much interest, okay, but knowing these properties will be useful for certain applications. Okay, so if we want to see the material classification based on their electrical properties, okay, I can classify the material in terms of whether a material is a conductor, okay, which is usually what all the metallic materials are there. Okay, for example, in our household application all the wires are made of copper, which is a very good conductor. Okay, sometime aluminum is also used because it is much cheaper than copper. Okay. And then one class of material which is a very important class in terms of electronic circuits and electronic applications, and this is semiconductors. Okay. So, understanding semiconductor is very important, that is what we will concentrate more in this lecture. Then there are insulators. Okay, of course, these are also important because if you have a conductor you have to have a insulation around that. Similarly, the insulators can be ceramic materials, for example, are usually insulator because of the covalent bonding, okay, or ionic bonding between the two atoms. Okay, there are no free electrons for conduction. But sometimes these ceramic material can show a very important property which is called superconductors. Okay. Now, the electrical conductivity is due to flow of charged particles. Okay. So, any conductivity will be related to movement of charged particles. These charged particles can be electrons or it can be ions also, or it can be charged holes. Okay. So, when electron leaves a valence band, it leaves behind one hole, okay, which can be considered as a positively charged hole, okay, or it can be combination of all these three. Okay. So, the conduction will depend upon the movement of these charged particles. The electrical conduction can be explained using band theory, that where the electrons are residing. Okay. So, in conduction depends on electrons in the conduction band. If the electrons are in the conduction band, then you will have a conductivity, otherwise you will not have. Okay. If the conduction is due to flow of electrons. So, the conductors are the ones which have valence band overlapping the conduction band. So, in case of conductors, what happens, the conduction band and the valence bands are overlapping each other. So, the electron in the valence band can easily go to the conduction band, and when you apply any electric field, the flow of electron will start. Okay. So, you have lot of free electrons there, okay, which are not bounded by the atom, okay, or they are not in the valence shell. So, they are free to move around, okay, because they are in the conduction band, and as soon as you apply any electric field they will move. Semiconductors are those which have a small gap between the valence and the conduction band, okay, but due to thermal excitation these electron can go from valence band to the conduction band. So, you can increase the conductivity of the semiconductor by taking it to higher temperatures, okay, where the thermal energy or the thermal excitation will push the electron from valence band to the conduction band. Okay. So, this is one of the important difference between the conductor and semiconductors, that the conductor or the conductors have lower conductivity at higher temperature. So, as you increase the temperature, the conductivity of a conductor will come down, whereas in case of semiconductors, when you take it to higher temperature, the conductivity increases, okay, because now more electron can go to the conduction band. In case of insulators, the electrons in the valence bands are separated by a large gap from the conduction band. Okay. So, between valence band and the conduction band there is a very large gap, okay, and they cannot jump from valence band to conduction band. So, that is why insulators do not conduct any electric charge. So, this is how if you see in terms of a graph, okay, that how these different bands are there. So, conduction band and valence band are there. So, in this case, this is the case for conductor. Okay. For conductor, the two are overlapping each other. So, the electrons in the valence band can easily go to the conduction band, okay, and they can carry the charge, okay, when an electric field is applied. Whereas in semiconductors, so this is for semiconductors, there is a small gap between the valence band and the conduction band, but the gap is quite small. So, that if you have any thermal excitation, the electron can jump to the conduction band. So, at 0 Kelvin of course, no conductivity will be there, okay, but at any higher temperature this conductivity will start increasing. In case of insulator, so this is for insulator, you will have a large gap between the two and it will not be able to for electron to jump to the conduction band. Okay. So, if you want to see the energy gap in terms of some values, semiconductors have energy band gap of less than 2 electron volts, whereas insulator have energy gap of more than 4 electron volts. Okay. In case of conductor, they are overlapping each other. So, there cannot be any gap between the two. Okay. So, on y axis the energy of electron is there. So, this is what is the band theory to explain the conduction in different type of materials, that why you have conduction in some material and not in some other materials. Okay. Of course, the theory is much more you have to understand more of that how the electrons are positioned in an atoms, in shells, in subshells, and there is a spin associated with each electron and so on. So, those are you have to go into much more details if you are interested only in the electrical properties of the material. Okay. For our purpose right now, this much information is sufficient to understand that we can have different type of materials and how the conductivity of different materials can change as a function of temperature, for example. There are other ways also to change the conductivity of the material, and that is what we will see in the next slides. So, if we come to semiconductor we will look slightly in detail, because these are one of the most important materials. In fact, all the electronic industry is based on only on the semiconductors, okay, that how you can manipulate the properties of the semiconductor. So, if you look at the semiconductor, there can be of two types. One is what we call as intrinsic semiconductors. Okay. So, in case of semiconductor, the valence and conduction bands do not overlap. Okay. However, electrons in the valence band can be excited to jump to the conduction band by thermal excitation, leaving behind holes in the valence band. Okay. So, when the electron goes from valence band to the conduction band, it leaves behind one hole in the valence band, okay, and that hole can be considered as a positively charged particle, okay, and electron is of course a negatively charged particle. So, these charge carriers are called intrinsic charge carriers, and semiconductor are called intrinsic semiconductors. So, this kind of small conductivity is always going to be there in the semiconductor because of the thermal excitation. Okay, that is why these are called, this is the intrinsic property of the semiconductor. Okay, that is why these are called intrinsic semiconductors. So, all semiconductors will have some conductivity if you are not at 0 Kelvin. Okay, at any other high temperature there has to be some conductivity in semiconductor, and in this condition it is called intrinsic semiconductor. So, for example, pure silicon or pure germanium will be of this type. okay, of intrinsic semiconductor type. Why they show this kind of property? Okay, that silicon have 4 valence electron. Okay, basically here it is shown. Okay, so one silicon atom is at the center and 4 are around it, and they are sharing their valence electrons to fill their outer orbit. So, please remember that I am not showing the full atomic structure of silicon here, I am just showing the outer orbit here. There will be 2 more orbits in this, okay, which I am not showing it right now, because it will complicate the whole schematic here. So, only I am showing the outer valence shell, okay, where the valence electrons are orbiting. So, one silicon atom in the center is sharing electrons with the 4, because in the outer shell it has only 4 electrons, it needs 8 electrons to be stable. That is why it is sharing with 4 other silicon atoms, okay, 1 electron to fill its shell with the 8 electrons and may become stable. So, with this silicon atom another 4 will come here, okay, and like that it will be a sharing of electron and covalent bonding will be there between the silicon atoms. So, in normal condition you will see that there is not going to be any free electron available for conduction, okay, but as the temperature increases, what happens that this electron may get sufficient energy, okay, to jump from this valence shell and leave behind a hole here and become free, okay, to carry a charge when electric field is applied. So, it can move when an electric field is applied, okay. So, because of thermal excitation it can jump from this shell and go out, okay. So, this is how the silicon arrangement is there, okay, and in this case when thermal excitation there has to be some intrinsic flow of charge will be there. The extrinsic semiconductor are the ones where you add deliberately some doping agents or doping elements, or this is what we call as doping of a semiconductor, to add elements of either a trivalent elements or pentavalent, okay. What do we mean by trivalent element? These are the element which has 3 electron in the outer shells, okay. For example, boron here is shown in the center, okay, it has these 3 let us say I think I have shown it by this red color electrons, these are for boron. So, you have 1, 2 and 3 electrons of in the valence shell of the boron, okay. So, these are the 3 valence electrons. So, this is a trivalent element, okay, which has 3 electrons in the outer shell. So, when you add this kind of element in the silicon, okay, and this is what we call as doping, then what will happen is the boron will replace the silicon atom, okay, and now what will happen, earlier all the silicon atoms were sharing 1 electrons and their shell were getting full with all the 8 electrons in the outer shell, okay, but now with the boron 3 electrons will be shared by these 3 silicon atoms, but with the 4th silicon atom it has no electron to share with. So, it is only having a hole present here, okay. So, with addition of each boron atom you will have 1 additional hole present here. Now, because it is not sharing any electron, this hole is not bounded by the bonding between the boron and silicon, okay. So, it is free to move, and as soon as you apply any electric field, this hole will move, okay. And since hole is considered as positively charged, okay, that is why these type of semiconductors are p type. So, if you add a trivalent element in semiconductor or silicon material, okay, you will get a p type semiconductor. When we dope the same intrinsic semiconductor with a pentavalent element, okay, we get a n type semiconductor where n stands for negative excess electrons, okay. So, again you can see antimony is there, okay, which has 5 electron 1, 2, 3, 4 and fifth one is now one extra electron is there. So, the 4 electrons is shared with the 4 silicon atom around it, one extra electron is there which is not shared with any electron. So, it is free to move now. So, we have increased the conductivity of the semiconductor by adding a trivalent element here, okay. And this free electron, when you apply electric field, it will be free to move. So, these are called extrinsic semiconductor when you add deliberately some element into that to make it either p type or n type. So, you need both p type and n type to make diodes and so on, okay, to make a circuit. So, both are important. Now, the superconductivity is another type of property where the material does not show any resistivity to electrical flow. Okay. So, you can understand for any flow of electricity through normal metallic materials, okay, there is always some resistance is offered to the flow of electric current. Okay, and of course, this is significant resistance, okay, and you have significant power loss because of this resistance. So, superconductors were, when people started thinking about that, the superconductor does not offer any resistance to electrical flow. Okay. So, and especially ceramics are some of these type of material which show superconductivity. So, these show very nil resistance, okay, at some temperature, but these temperature are usually much lower. So, like at liquid nitrogen and these kind of temperatures, or below that they show superconductivity. Okay. So, the resistivity, the temperature at which the resistivity completely become 0 is called the critical transition temperature TC. Okay. Many metals and ceramics and intermetallic show this kind of properties, very important, and these kind of maglev high speed trains, you must have heard of these trains, maglev high speed trains, they operate on this principle, okay, that when you have superconductor and you put another conducting metal over that, then it will kind of float over that. Okay. There are a lot of theories about that. Okay. We are not going into details of that, but these are some important class of materials now to have zero friction movement of, for example, in this case trains, okay, by having a superconductivity in the where the wheels are there. Okay. Then coming to magnetic properties, the magnetism can be divided into different classes. Okay. A diamagnetism is a very weak magnetism which exists in the presence of an external field. Okay. So, when you apply the external field, only then you will see magnetism in the material, and when you remove the external field, then there will not be any magnetism. Then there can be paramagnetism, slightly stronger than diamagnetism. Okay. In presence of external field, dipoles line up with the field. So, again in the presence of external field, you will see some magnetism, it will be slightly stronger than diamagnetism. Ferromagnetism is the one which you usually see in magnets, whatever you use in your, for example, in your music box. Okay, there will be some magnet is there going to be there. Okay, and lot of for example, your fridge magnet, you will have a magnet. So, all these magnet are show ferromagnetism, which is very strong magnetism they show, because the dipoles line up permanently upon application of external field. So, when you apply the external field, okay, they permanently show magnetism. So, ferromagnetism will always show magnetism once you have induced the magnetism in that in that particular material. For example, if you might have seen there are sometime on the office table some jar is there to store the pins, all pins, and there is a magnet around it, then the all pin also start showing magnetism after some time. Okay, so under an external field they get magnetized and they will remain magnetic even after removal of the external field. Then antiferromagnetism are there. Okay, so dipoles line up in opposite direction resulting in zero magnetization. So in this case if you apply the external field also, you will not get any magnetism. Okay, so these are antiferromagnetism. So anti of what we have discussed just now. A magnetic dipole is a small magnet composed of north and south poles. Okay, so basically for any magnet we have already seen that you will always going to have some south and north pole. Okay, so the dipole, when we say magnetic dipole, okay, basically we are talking about an arrangement where they are arranged in this fashion, south and north. So if all the dipoles are arranged in the same fashion, okay, then you will have magnetism. Okay. So in any ferromagnetic material, we will now consider basically ferromagnetic materials only here. Okay, magnetic dipoles are divided into domains. Okay, so if you take any material, there will be some domains will be there. Okay, like grain boundaries or grains. Okay, in material, where in one domain the dipole will have one type of alignment. Okay, in another domain they may have a different alignment, for example. Okay, again those dipole north south dipoles, and maybe another domain they will have another alignment and so on. Okay, these are not grain boundaries, these are domain boundaries. So one domain can consist of, so this can be a domain can be within one grain. So you can have one grain like that. In this one grain you can have domains like this, okay, within a grain itself. So they are not divided between the grain. Single grain can have multiple domains, okay, and each domain you will have some alignment of dipoles. So when it is not magnetized, in each domain the dipoles are aligned in one direction, but between two domains alignment will be different. Okay, so in a domain the alignment is going to be same, but if you compare between two domains the alignment is going to be different. So when it is not magnetized, in all these domains they are aligned in a very random way. Okay, but when you do a magnetization, okay, during magnetization dipoles in all the domain start aligning in one direction. Okay, so when you do magnetization, all these domains will start aligning in one direction. So which can be shown by a curve like this, where it is called a BH curve, where B is your flux density, which is we are inducing the magnetic flux density in the material, M, or you can say M also magnetization, H is the field intensity. I am sorry, there is the spelling is wrong here. So field intensity is there, H, okay, on the x axis. So this is what externally we are applying on the material, and MS is the saturation magnetization. Okay. So what happens when you start applying a magnetic field on a material? Okay. So initially they have these domains, and alignment of dipoles will be different in each domain, and you started applying some magnetic field on this material for magnetization. Okay. What will happen, that slowly the flux density, the magnetic flux density will increase in the material as a function of H, the external applied field intensity. So you can see that slowly the domains are started changing. So some domains are disappearing, okay, and as the H is increasing, B is increasing, you reach a saturation point when all the domains are disappeared, and throughout the material you have only one alignment of dipole which is in this direction. Okay. So as I told you, in all the case the alignment is same, north south, north south, north south, and so on. Okay. So now when all the alignment of the dipoles is in the same direction, so one end will be a south pole, another end will be a north pole, okay, and you will have a magnetization in the material. So when the whole material is of one alignment, then you have reached the saturation. Now you cannot do anything else. Okay, you can keep increasing the external field, but you cannot go beyond that. All the dipoles are in one alignment. So you have reached the saturation point. So this is my saturation magnetization. Okay. Now, once you do that, what happens when you again bring down the magnetic field? Okay, that is of interest for us, because that actually bring about a phenomena called hysteresis. Okay, and that is important for our material application. So, the hysteresis, what do we mean by hysteresis? Okay. So, when you start the from this point, okay, when the material was not magnetized, okay, you applied an external field and you started the magnetization process, okay, and it reached the saturation magnetization. Okay. Now, you are reversing the field. Okay. So, suppose you apply a field such that a given component, okay, suppose something like this, by applying an external field. Now, this is what is the dipoles are aligned such that you get these two poles in the material, and now you have reversed the external field. What will be will happen that the dipole will again align in the different direction, and the north has to become south and south has to become north. So, all the domains have to align in the opposite direction now. Okay. So, we are reversing the field now here. Okay. So, you can see that we started from 0 for external field when the flux density was 0. Okay. But while reversing, what we have seen that when my external field is 0, still there is some magnetization in the material is left. That means, all the domains could not get aligned into the opposite direction. Okay. So, there is some remnant flux will be there, though my external field is 0 now. Okay. So, this remnant flux is called, of course, remanence. Okay. Because this much has remained in the material, because all the domains could not get aligned in the opposite direction when we reverse the field. So, while reversing at h is equal to 0, some of the domain still remained aligned in the previous direction, which we did while magnetizing, which gives rise to a residual magnetization, which is called remanence MR. Okay. So, that much will remain in the material. To get rid of this magnetization, we have to now go into the negative direction of the electrical field. Okay. And this is how much negative we have to go will be given by Hc. So, to reduce the field B or magnetization to a 0. Okay. So, now we have come to the 0 flux, the flux density in the material. Okay. Reverse field of Hc is applied. So, negative of this external field is applied, which is called coercivity. So, basically you are coercing the material to bring down the flux density to 0. Okay. So, you are forcing the material. Okay. So, because you are coercing it, this is called coercivity, and this much negative energy, negative external field you have to apply to bring it down to the earlier state from where we started. So, these are the two very important properties of any magnetic material, that what is the remanence value and what is the coercivity value. Okay. And this happens during the field reversal. So, again you can go into the negative direction as you went into the positive direction here. Again you will reach a saturation. Now, all the domains are reversed and they are aligned in the reverse direction. So, again you will reach a saturation point. Okay. And when again you start reversing the field, okay, you will see that some remanence field will be there, some coercivity will be there. That means, some positive external field has to be applied to bring it to 0 flux density again, and then it will go back to the saturation. Okay. So, you can see that in each of this cycle, okay, you are losing some energy. So, there is an energy loss in each of this cycle, okay, because it is not following the same. If it would have followed the same curve, okay, maybe it would have gone like this, and again as you reverse the field it will go like this, then there will not be any problem, then it will not lose any energy in the this process of magnetization, demagnetization and so on. Okay. Now, depending upon this hysteresis loop, okay, so the area within the hysteresis loop represent magnetic energy loss per unit volume per cycle. So, in each cycle you lose an area an energy given by the area of this loop, okay, because this much extra energy you have to apply to bring it back to 0 and then take it to the negative side and so on. So, in each of these cycle, when you do the magnetization, demagnetization, then go into the negative direction, okay, you lose a certain amount of energy which is equal to the area of this loop. So, now depending upon this area of the loop, I can define two types of material. One is soft magnetic material, another is hard magnetic material. Okay. So, soft magnetic materials have narrow loop. Okay. So, this is a soft magnetic material. That means you can have these are easy to magnetize and demagnetize. I can easily magnetize them and demagnetize them because you will have smaller remanence, you will need a smaller coercivity and so on. Okay. So, it can be easily done, and these are actually, that is why important for transformers. Okay. So, you can understand in transformer, okay, you have primary winding. So, for example, suppose you have a transformer like this. So, you have primary winding here, okay, and you have secondary winding here, okay, and in the primary winding an alternating current is flowing which has a cycle of 50 hertz, okay. That means 50 times it is becoming positive and negative, okay. So, this core material will also get demagnetized, this whole cycle will be repeated 50 times in a second, okay. 50 hertz means 50 times this hysteresis loop is being you are doing in the material, okay. So, in each cycle you are losing certain energy, okay. That means there is a big loss of energy during the when you are stepping down or stepping up the voltage, okay, using transformer. That is why the transformers are covered with oil, okay. They are submerged in oil to take out all this heat, and you must have seen on the transformer outer surface also there are fins, okay, to increase the surface area so that this heat can be dissipated, and sometime you must have seen that the transformer also burn up, okay, because there is so much heat is generated. So, you can understand the importance of hysteresis loop, that I have to have material which has a smaller hysteresis loop, okay, and these are called soft magnetic materials. A lot of research goes in the making of this type of material. One of the most important material which is used for this transformer applications are silicon steels, which contains around I think 2 to 3% silicon, okay, and they show this kind of soft magnetic properties, okay. Now, hard magnetic materials are also important, okay. They of course have high remanence, okay. They have higher coercivity, saturation magnetization will also be higher, okay, and that is why they have higher loss of energy. But for materials where you do not want to keep changing their magnetization condition, okay, these are important. So, in permanent magnets we will use hard magnetic materials, because in this material once we have magnetized it, we want it to remain like that, okay. So, if it has a higher saturation magnetization, then it is good, the magnetic field which it is going to generate will be of higher value, okay. So, for permanent magnets we want to have hard magnetic materials. So, with that we have covered two very important class of materials, electrical magnetic materials, okay, and we have seen few properties of these materials which are of great importance to our day to day life, okay. So, with that I would like to say thank you, okay.